In our final video, we will look at Johansson's procedure to determine the cointegration rank H, so the number of cointegration relations we have. We saw in the previous video that the log likelihood depends on H, since we had H eigenvalues entering. Intuitively, what we could do to determine H is to look at how the log likelihood improves or deteriorates if we would change the number of cointegration relations H. In our lecture on VARs, we saw that the likelihood ratio test is very convenient here when we can compare values of the log likelihood. And that is also what we will do. We will resort to two likelihood ratio tests for determining the number of cointegration relations, the trace test and the max eigenvalue test. So let's start with the trace test. Let's say that we want to test the null that we have H cointegrating vectors versus the alternative that we have a stationary var, which would mean that we have n cointegrating vectors, as we saw last week. The likelihood ratio test would then look at the difference in log likelihood when we have n versus H cointegration relations. Now, in this case, the expression for the log likelihood was very easy, as I copied over in this box. So if we would need to look at the difference between the log likelihood when we have n versus H cointegration relations, then what would this difference be? Well, the first terms here would all be identical, so they would vanish. And it's all about this last sum over here. In the case that we have, let's say, n cointegration relations, then that sum would go up from I equals to 1 up until n. Versus if we need to compute the log likelihood for H cointegration relations, then that sum would go up from I up until H, I1 up until H. So the difference then concerns indeed the eigenvalues from H plus 1 up until n. Now let's pause here for a minute and think about what would happen under the null. So under the null, if we have H cointegrating vectors, then the first H eigenvalues would matter and all the remaining ones would be 0. In practice, they would of course not need to be estimated and they will not be equal to exactly 0, but these remaining eigenvalues will be small. And so we would have here a sum of these logs that are close to 1 because the lambda heads are small. And so then the test statistic would also be small. And indeed, as always here for the likelihood ratio test, we would not reject the null for small values of the test statistic. How to perform inference? Well, the asymptotic distribution of the test statistic is given by the trace of this guy over here. Hence the name trace test. You again see Brownian motions popping up since we have non-stationarity, but we won't go over the details here in detail. Critical values are tabulated in software packages such as R. What is more convenient and important for us to know is how we should use this trace test in practice to determine the cointegrating rank. Well, we should perform a sequence of tests, starting from the initial null hypothesis that we do not have cointegration, so that H is equal to 0. If we would not reject the null, then we would conclude that there is no cointegration and we stop. If we do reject the null, then we need to continue. There seems to be evidence that there is cointegration, but we don't know how many relations yet. So that's why we need to continue to the next step. Where in the next step, we test the null that there is at most one cointegration relation. The procedure would stop if we would not reject the null. Then we conclude that there is one cointegration relation. Otherwise, we continue again until we possibly arrive all the way at this last step where we test the null for n-1 cointegration relations. So the trace test is the most popular test that is used to determine the co-integration rank, but there is also an alternative one, namely this maximum eigenvalue test. It has the same null hypothesis, but another alternative hypothesis, namely that there are H+1 co-integration relations. So the test has power against a different alternative. The test statistic would again be given by the difference between the maximized log likelihood for H+1 versus H co-integration relations. So it's hopefully then not a surprise that only one eigenvalue pops up over here, as also the name gives, namely this last, the maximum eigenvalue. And again, under the null, we expect that this eigenvalue will be small, so we would not reject the null for small values of the test statistic. And we can then perform the same sequence of tests as we did for the trace test. But so in general, since we have a different alternative hypothesis, it is possible that the trace and the max eigenvalue test stop at another point in the sequential procedure. And this points towards a different conclusion than possibly concerning the co-integration rank. Now we looked into maximum likelihood derivations and how to determine the co-integration rank. I've included some final couple of slides on a short empirical illustration to get you started on VECM analysis in R. And I have a small example on housing in the US. So two non-stationary time series, the number of housing starts and the number of housing completions. Clearly, they are non-stationary. Our first step would also be to perform unit root tests on them, but they do indeed point towards the fact that both series are integrated of order 1, which makes it interesting to investigate whether they are co-integrated. First, we start by determining the co-integrating rank. And for that, we actually need to know how many lagged differences P-1 we need to include in our VECM. Remember, this P was the order of our var in levels. So we could use information criteria via the var select function on the series in levels, importantly, to determine what P could be. AIC points here towards a different solution than BIC. I continue in this example just with taking the order as indicated by BIC, namely 3 lags. Next, let us compute the trace statistic in R. We perform co-integration analysis with Johansson via this function over here. You can use this function from the URCA library. We need to specify the series in levels as an input. And we ask for the trace test statistic, and the input parameter K corresponds here to the P from the slide, so the order of the var in levels. Note that this function does not work for values of K smaller than 2. So in case your var select would have set the order to a value less than 2, you would still need to put K equal to 2 over here. And this argument over here simply means that we will include a constant term in our co-integration relation, and the transitory specification corresponds to the VECM representation from the lecture slides. Now the output from the test is reported over here, and you should read it from bottom to top. Because first we test the null of no co-integration, so co-integration rank R equal to 0. The value of the test statistic is given over here, and since the value of the test statistic exceeds the 5% critical value, we reject the null hypothesis that there is no co-integration. And so we should continue testing for at most one co-integration relation. Here, the value of the test statistic does not exceed the critical value at the 5% level. And so our procedure stops And we conclude that there is one cointegration relation. You could also have opted for the maximum eigenvalue test instead of the trace specific, where only this argument changes and the output is shown on this slide. You can verify for yourself again that in the first step where we test the null hypothesis of no cointegration, that we reject the null. And we do not reject the null in the second step of the procedure. So also here, we conclude that the cointegration rank is 1. Finally, you can continue with estimating the vector error correcting model through this function over here. It takes in your object from the previous slide as an input, and you specify how many cointegration relations there are. How is the output organized? Well, you have here as many columns as you have time series, so 2 in our case. And each column corresponds to an equation in the vector. First, you have the adjustment coefficient in front of the error correcting term, which is beta prime times the lagged y. Then you have the coefficients in front of the lag differences as denoted by dl over here. So first lag and the second lag. Here in the second slot for beta, you also have information on the cointegration relation through the estimate of beta. And it collects the coefficients of your series in the cointegration relation, which you can then report and interpret. On the next slide, for convenience, I copied over the estimates from the previous output slide in terms of the Vecam notation from the slides. So you can match up the R output with these slides. All right, so that brought us to the end of this lecture, also to the end of the course. You should be able to prepare for the last brief tutorial after having seen these videos. Good luck.